Stop right there, look at that sky. For 400 years, every single astronomer, physicist, and cosmologist on this planet has been looking at the universe, and we have all been wrong. Not a little wrong. Not wrong about a minor detail. Wrong about the most fundamental thing you can be wrong about: the age, the size, and the very structure of everything that exists. And we know this because of one machine, one telescope, floating in the cold silence of space 1.5 million kilometers from Earth. A machine that has done something no instrument has ever done before. It has made the universe contradict itself. The James Webb Space Telescope, a telescope so powerful it can see the light of galaxies that formed just 300 million years after the Big Bang, has been sending back images that should not exist. Galaxies that are too big, too old, too perfectly formed, too impossible. And here is what a senior NASA astrophysicist, Dr. Alison Kirkpatrick of the University of Kansas, said when she saw the first Webb data. She said, and I quote directly, "I was absolutely shocked. They are so massive that we should not even find them according to our current cosmological models. Something is really, really off. Something is really, really off." Those words, spoken by a credentialed NASA-affiliated scientist, represent the most profound admission in modern cosmology. Because the model they are talking about, the model that is now really, really off, is the Lambda CDM model, the standard model of cosmology. The very framework that every textbook, every documentary, every NASA press release for the last 40 years has been built upon. If they were wrong about that, what else are they wrong about? Everything. And that is what this video is about. Now buckle up, because what I'm about to take you through over the next few hours is going to change the way you look at the night sky, forever. Before we can understand what James Webb broke, we need to understand what we built. So let us go back to the beginning, not the beginning of the universe, but the beginning of our confidence that we understood it. The year is 1929. An astronomer named Edwin Hubble, yes, the man the original Hubble telescope was named after, makes an observation that rewrites everything. He notices that distant galaxies are moving away from us. And not just moving away, they are moving away faster the farther they are. The universe is expanding. This single observation, made at the Mount Wilson Observatory in California, gave birth to what we now call the Big Bang theory. If the universe is expanding, then in the past it must have been smaller. Wind the clock back far enough and everything, every galaxy, every star, every atom, every thought you have ever had, was compressed into a single, infinitely hot, infinitely dense point. And then, approximately 13.8 billion years ago, it exploded outward. For most of the 20th century, this framework was challenged, tested, refined. By the 1990s, cosmologists had built what they called the Lambda CDM model. Lambda for dark energy, CDM for cold dark matter. This model predicted a very specific history for the universe. A timeline, a recipe, a sequence of events that, if correct, means the cosmos evolved in a highly specific, well-understood way. Here is what the Lambda CDM model told us with enormous confidence. After the Big Bang, the universe was a hot, featureless soup of energy and particles. It took roughly 380,000 years for it to cool enough for atoms to form. Then began what cosmologists call the cosmic dark ages, a period of hundreds of millions of years where there were no stars, no light. Nothing but hydrogen and helium gas slowly clumping together under gravity. It was not until about 400 million years after the Big Bang that the very first stars and protogalaxies began to ignite. And crucially, these early structures had to be small, tiny, fragile, primitive, because there just was not enough time for gravity to do its enormous work of assembling large, complex galaxies. You cannot build a skyscraper in a day, and you cannot build a massive, structured galaxy in 300 million years. That was the consensus. That was the model taught in every university. That was the cosmology presented in every documentary Morgan Freeman ever narrated. It was wrong. But here is the thing. To understand why it was wrong, you need to understand how we got so confident in the first place. And that is where a series of extraordinary experiments comes in. In 1964, two physicists at Bell Labs, Arno Penzias and Robert Wilson, accidentally discovered the cosmic microwave background radiation, the CMB. This is the faint echo of the Big Bang itself, ancient light that has been traveling through space for 13.8 billion years, stretched by cosmic expansion into microwave frequencies. It is literally the oldest light in the universe, and it is everywhere. If you tune an analog television to static, a small percentage of that noise is actually the CMB. You are watching the afterglow of creation. The CMB gave cosmologists an extraordinary gift, a snapshot of the infant universe, and from studying its tiny temperature fluctuations, mapped with incredible precision by NASA's WMAP satellite and later the European Space Agency's Planck satellite, scientists derived their best estimate of the age and composition of the universe, 13.8 billion years old, roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. These numbers became scripture, the gospel of Lambda CDM, and then James Webb arrived, and the gospel started to unravel. Let me tell you about the most expensive, most delayed, most incredibly powerful telescope ever built by human hands, the James Webb Space Telescope. Total cost, approximately $10 billion. Time from concept to launch, more than 25 years. Weight, 6,500 kilograms. Primary mirror diameter, 6.5 meters, made of 18 hexagonal gold-plated beryllium segments that unfold in space like a flower opening in slow motion. It launched on Christmas Day 2021 on an Ariane 5 rocket from the Guyana Space Center. It traveled for 30 days, then unfurled itself at Lagrange Point 2, a gravitational sweet spot 1.5 million kilometers from Earth, where the gravitational pull of the Sun and Earth balance perfectly, allowing Webb to orbit in sync with Earth while always facing away from the Sun. Why does its position matter so much? Because Webb is an infrared telescope. It detects not visible light but heat, infrared radiation, and infrared detectors must be kept extraordinarily cold, colder than 50 Kelvin, which is minus 223 degrees Celsius. If any warm object, the Sun, the Earth, the Moon, got in its line of sight, the thermal noise would drown out the faint infrared signals from the distant universe. Webb's sunshield, the size of a tennis court, keeps it in permanent cold shadow. Now here is why infrared matters so profoundly. You have heard of the Doppler effect, the way a police siren sounds higher pitched as it approaches and lower pitched as it moves away. Light does the same thing. When a galaxy is moving away from us, as all distant galaxies are because of cosmic expansion, its light is stretched toward the red end of the spectrum. Astronomers call this red shift. The farther away a galaxy is, the faster it is receding, and the more red-shifted its light becomes. A galaxy from 13 billion years ago is so highly red-shifted that its light, which started as ultraviolet or visible, has been stretched all the way into infrared wavelengths. The Hubble Space Telescope, operating in visible and ultraviolet light, literally could not see these galaxies. Webb, operating in infrared, can. This is the key. Webb is not just a bigger, better Hubble. It is a fundamentally different kind of eye. It is looking at a part of the electromagnetic spectrum that no previous space telescope could adequately explore. And what it found there shook the foundations of cosmology. Webb began its science operations in July 2022. Within weeks, the data started coming in that caused senior astrophysicists to go pale. The first bombshell was a paper published in February 2023 in the journal Nature Astronomy. Led by Dr. Ivo Laber of Swinburne University of Technology, the study identified 6 candidate galaxies, massive red structured galaxies at redshifts between 7 and 10. That means they existed between 500 and 700 million years after the Big Bang. These galaxies appeared to have stellar masses, that is, the combined mass of all their stars, equivalent to as much as 100 billion times the mass of our own Sun. Some appeared to be as massive as the Milky Way, which took billions of years to assemble. Dr. Laber himself described the findings this way. It's like you're building blocks of Lego. You have these little bricks that come together slowly. But what we found is like someone handed us a completed Death Star on day 1. It should not be there. Now, scientists are cautious people. The first reaction in the field was, Maybe these are not real. Maybe these are instrument artifacts. Maybe we are misidentifying the redshift. Maybe there are contaminating light sources inflating our mass estimates. So teams around the world spent months doing follow-up studies. They used Webb's near-spec spectrograph, an instrument that breaks a galaxy's light into its component wavelengths and identifies chemical signatures, to get confirmed spectroscopic redshifts. You cannot fake spectroscopy. The absorption lines from hydrogen, oxygen, and carbon do not lie. The galaxies were real, the redshifts were confirmed, the masses were real, and the model was wrong. What if I told you that the universe is simultaneously expanding at two different rates, depending on how you measure it? I know that sounds impossible. How can a single physical reality have two different expansion rates? It cannot, which means one of two things. Either our measurement techniques are wrong, or there is a profound fundamental error somewhere in our understanding of physics. This is the Hubble tension, and it has been building for years, but James Webb has now made it dramatically worse. Let me explain. There are two main ways to measure the expansion rate of the universe. A number called the Hubble constant, symbolized as h0, measured in kilometers per second per megaparsec. In plain English, for every roughly 3.26 million light-years of distance between us and a galaxy, that galaxy is receding from us by h0 kilometers per second. Method 1. Look at the early universe. Use the cosmic microwave background, the ancient light from 380,000 years after the Big Bang, to calculate the expansion rate from first principles. This was done exquisitely by the Planck satellite mission, completed in 2018. Their answer, h0, equals approximately 67.4 kilometers per second per megaparsec. Method 2. Look at the nearby universe. Use observable distance markers, specifically a type of star called Cepheid variables and a type of exploding star called type Ia supernovae, to measure distances and recession speeds directly. The leading team doing this, the SHAG-0ES project led by Nobel laureate Dr. Adam Rees of Johns Hopkins University, gets a very different answer, approximately 73 kilometers per second per megaparsec, 67.4 versus 73, a difference of about 8%. In cosmology, 8% might sound small. It is not. These measurements have been refined to extraordinary precision. The statistical uncertainty in each measurement is now less than 1%. The two values are incompatible at a statistical significance of more than 5 sigma. In physics, 5 sigma is the gold standard for declaring a discovery real. The discrepancy between these two measurements of the Hubble constant is so statistically significant that by the standards of physics, it is as real as the discovery of the Higgs boson. Where does James Webb come in? The tension was already serious before Webb, but one of the key hopes was that maybe the Cepheid-based measurements had a calibration error, something subtle in how astronomers were measuring the brightness of those variable stars. Webb's extraordinary resolution and infrared sensitivity were supposed to resolve that. If the Cepheid measurements were contaminated by nearby stars or dust, Webb would reveal it. In 2023, Dr. Adam Rees and his team published a landmark Webb paper. They used Webb to re-examine Cepheid variables in nearby galaxies with resolution and depth impossible for Hubble. The result? The Cepheid measurements were solid. The calibration was not the problem. The tension did not go away. It hardened. Rees stated publicly, "With Webb, we can now rule out measurement errors as the source of the Hubble tension with very high confidence. This is likely either a systematic in the early universe measurements or new physics." New physics. Those two words should send a chill down your spine. New physics means our equations are incomplete. It means Einstein's general relativity, the most tested, most precise physical theory in history, may be missing a term. It means dark energy, the mysterious force accelerating the expansion of the universe, may not be what we think it is. It may be changing over time. It may have a different value in the early universe than it does today. There is a secondary possibility that is even more radical. Maybe the standard cosmological model has a fundamental structural error that propagates into both the CMB analysis and the supernova analysis. Maybe something we are treating as a constant is not a constant. Maybe the universe has slightly different physics in different regions. Maybe we are missing an entire component of the cosmos, some form of energy or matter we have never detected, that was important early on and invisible now. Whatever the answer, we do not have it yet. And for the first time in a generation, mainstream cosmology has had to admit it is standing at a crossroads. Here is a question that will reframe everything you are about to hear. What shape should a very young galaxy be? Think about it intuitively. The early universe was chaotic. The first structures that formed after the Big Bang were irregular clumps of hydrogen and helium gas, pulled together by dark matter's gravitational influence. As these protogalactic clouds collapsed under gravity, they should have been turbulent, asymmetric, blobby, merging and colliding with each other. The beautiful disk galaxies we see today, the grand spirals with their elegant arms, their thin, flat structures, their organized rotation, those should only emerge after billions of years of gravitational settling. Like a spinning figure skater slowly pulling their arms in until they spin in a perfect, balanced form. The Standard Model predicted that the early universe should be full of what astronomers call irregulars and protogalactic fragments, messy, asymmetric, still assembling structures. Clean, organized disk galaxies should be rare or absent before about 5 billion years after the Big Bang. Webb looked, and Webb found something else entirely. A study published in 2023 in the astrophysical journal Letters, led by Dr. Lior Shamir of Kansas State University, analyzed thousands of galaxies imaged by the Webb telescope's first deep field observations. The result was startling. A significant fraction of galaxies at very high redshifts, galaxies existing just 1 to 2 billion years after the Big Bang, already show clear disk morphologies, flat, rotating, organized structures. But it gets stranger. A follow-up analysis by Shamir's team found something even more unexpected in these early disk galaxies. They appear to rotate preferentially in one direction. When looking in one direction of the sky, more galaxies have clockwise spin. In another direction, more galaxies have counterclockwise spin. This asymmetry, which should not exist if the universe is isotropic and homogeneous on large scales, as the Standard Model demands, suggests the universe may have a large-scale structure that violates a principle cosmologists call the cosmological principle. Now, a word of scientific caution here. The Shamir results are controversial. Other researchers have questioned the statistical methodology. Some argue the asymmetry could reflect instrumental biases or analysis artifacts. This is exactly how science should work. Contested findings, peer review, replication, and that debate is ongoing. But the disk galaxy problem itself, the sheer number of organized, flat, rotating galaxies at early cosmic times, is much more solidly established and widely accepted in the community, and it remains deeply puzzling. One possible explanation that is gaining traction: maybe the Standard Model systematically underestimates how quickly primordial gas clouds can lose their angular momentum and settle into rotating disk structures. There may be physical processes, possibly related to the role of dark matter halos, or feedback from early supermassive black holes, that organize galactic structure faster than we thought. Which brings us to another Webb revelation: supermassive black holes. In our models, supermassive black holes, the monsters at the center of galaxies with masses millions or billions of times that of our Sun, are thought to grow gradually through a process of accretion. They pull in surrounding gas, form what is called an accretion disk, and slowly grow over billions of years. Some of the most massive ones in the universe are thought to have taken most of cosmic history to reach their enormous sizes. Webb has found supermassive black holes at redshifts corresponding to just a few 100 million years after the Big Bang, cosmic infants already enormous. One example is GN-Z11, initially discovered by Hubble, but studied in unprecedented detail by Webb. GN-Z11 is a galaxy seen as it existed just 430 million years after the Big Bang. And at its center sits a black hole, feeding at a rate so ferocious it is 5 times higher than the theoretical maximum rate for its mass, what physicists call the Eddington limit. There are several competing explanations. Perhaps the first black holes formed not from dying stars, as in our current model, but directly from the collapse of massive gas clouds in the early universe, what are called direct collapse black holes, or DCBHs. These would be born big and grow fast. Perhaps in the dense early universe, black holes could sustain super Eddington accretion for long periods, eating matter far faster than our models allow. Or perhaps our model of how the early universe seeded the first black holes is simply wrong from the start. Each of these explanations requires revisions to our standard picture, and all of them are active areas of research right now, driven by Webb's data. Dark matter, you have heard the term. It is one of the most familiar concepts in popular cosmology. And yet, here is the extraordinary thing: we have never seen it. Not once, not directly, not with any instrument ever built, including James Webb. Let that sit for a moment. 27% of the mass-energy content of the entire universe is composed of something that does not emit light, does not absorb light, does not reflect light, and does not interact with any of the four known fundamental forces except gravity. We call it dark matter because it is dark to us, invisible. And we know it is there for one reason only: the things around it move as if it is there. The first serious evidence for dark matter came from astronomer Fritz Zwicky in 1933, who noticed that galaxies in the Coma cluster were moving too fast. They should have flown apart unless there was far more mass holding them together than we could see. Then in the 1970s, astronomers Vera Rubin and Kent Ford measured the rotation curves of spiral galaxies and found something that should not exist. Stars at the edges of galaxies were orbiting just as fast as stars near the center. In any normal mass distribution, like our solar system, where outer planets orbit slower than inner ones, they should have been moving much slower. The only explanation: a vast, invisible halo of mass enveloping each galaxy. For decades, the leading candidate for dark matter was a class of particles called WIMPs, weakly interacting massive particles. These are theoretical particles with masses comparable to atomic nuclei that interact via the weak nuclear force and gravity only. The beauty of WIMPs was that they arose naturally from several extensions of the standard model of particle physics, particularly supersymmetry. If supersymmetry is correct, WIMPs should exist, and if WIMPs exist, they should be detectable. For 3 decades, physicist after physicist built increasingly sensitive underground detectors, chambers of liquid xenon or germanium, buried kilometers underground to shield them from cosmic ray interference, waiting for the signal of a WIMP bouncing off an atomic nucleus. The Large Underground Xenon Experiment, the Xenon 1T Experiment, Panda X, Li X, all extraordinarily sensitive, all returning the same result: nothing. Silence. No WIMPs detected. The Large Hadron Collider at CERN, the most powerful particle accelerator ever built, was partly designed to produce dark matter particles directly. Proton collisions at energies of 13 trillion electron volts, millions of collisions per second. For years, no dark matter particles. Now, absence of detection does not mean absence of existence. Detectors have limits, and theoretical models have parameter space. But the silence is increasingly uncomfortable. The simplest, most natural WIMP candidates have been essentially ruled out at the masses and cross-sections where theory most strongly predicted them. And this is where James Webb enters the dark matter crisis. Webb's observations of galaxy clusters have given us extraordinary new gravitational lensing maps. Measurements of how the mass of galaxy clusters bends the light of background objects. Gravitational lensing is the best probe of dark matter distribution we have because it responds to all mass regardless of luminosity. And what Webb's lensing maps show is that dark matter in early universe structures appears to be distributed differently than our best computer simulations, the Millennium simulation and Illustris TNG, predict. The simulations, based on cold dark matter, slow-moving particles, predict dark matter should form dense cusps at the centers of galaxies. Observations consistently find cores instead, more spread-out distributions. This is the famous core cusp problem, and it has been nagging cosmologists for 2 decades. Webb has sharpened the problem rather than resolved it. Some theorists are now proposing alternatives to cold dark matter. One gaining serious traction is called fuzzy dark matter, or ultra-light axion dark matter. Instead of heavy WIMP particles, fuzzy dark matter consists of extraordinarily light particles with masses around 10 to the minus 22 electron volts, so light that quantum mechanical effects operate at the scale of entire galaxies. In this model, dark matter behaves less like particles and more like a wave, a quantum fluid pervading the universe. The wave nature of fuzzy dark matter would naturally suppress the formation of dense central cusps and produce smoother galactic cores, potentially resolving the discrepancy. And then there is the most radical proposal of all, modified Newtonian dynamics, or MOND. The idea, first proposed by physicist Mordechai Milgram in 1983, that dark matter does not exist at all, that instead our equations for gravity are wrong at very low accelerations, that Newton's second law, force equals mass times acceleration, needs a modification in the regime of extremely weak gravitational fields, the regime that applies to the outer reaches of galaxies. MOND has had extraordinary successes. It naturally predicts the Tully-Fisher relation between galaxy luminosity and rotation speed, without any free parameters. It correctly predicts rotation curves for isolated galaxies with remarkable accuracy. But it struggles with galaxy clusters, where more mass energy than MOND predicts seems to be required. A relativistic extension called MOND, called tensor vector scalar gravity, developed by physicist Jacob Bekenstein, and more recently a framework called covariant emergent gravity by Eric Verlinde, are attempting to build full cosmological theories that replicate dark matter's effects without actual dark matter particles. Is dark matter real, or is it an artifact of incomplete gravitational physics? 30 years from now, cosmology textbooks will have an answer to this question. Right now, we genuinely do not know. In 1917, Albert Einstein made what he would later call the greatest blunder of his scientific life. Working out the predictions of his newly published general theory of relativity, he realized something troubling. His equations predicted that the universe could not be static. It should either be expanding or contracting. Since no expansion or contraction had been observed, Einstein added a term to his equations, the cosmological constant, denoted lambda, a kind of repulsive energy built into the fabric of space itself that would counteract gravity and allow a static universe. When Hubble discovered cosmic expansion in 1929, Einstein removed the cosmological constant. Blunder, he said, unnecessary modification. Then, in 1998, two independent research teams, the Supernova Cosmology Project led by Saul Perlmutter, and the High-Z Supernova Search Team, led by Brian Schmidt and Adam Rees, made a discovery so shocking they initially did not trust their own data. They were studying Type Ia supernovae, thermonuclear explosions of white dwarf stars, which serve as standard candles because their intrinsic luminosity is precisely known. By comparing their apparent brightness to their known true brightness, astronomers can calculate their distance with high precision. What Perlmutter, Schmidt, and Rees found was that distant supernovae were farther away than they should be. The universe's expansion was not just continuing, it was accelerating. Something was pushing space apart with increasing vigor, overcoming gravity, making distant galaxies recede from us faster and faster as time went on. Einstein's cosmological constant, his greatest blunder, was suddenly back. Not as a static stabilizer, but as a dynamic driver of cosmic acceleration. This mysterious energy driving the expansion was given the name dark energy. In 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for this discovery. The discovery that 68% of the entire mass energy content of the universe is composed of something we have absolutely no physical explanation for. The simplest interpretation is that dark energy is vacuum energy, quantum mechanical fluctuations of empty space, where particle-antiparticle pairs constantly flicker into and out of existence, contributing a small but non-zero energy density to the vacuum. This is the cosmological constant interpretation. Lambda is a fixed, unchanging energy density of the vacuum. The problem, when physicists calculate what the vacuum energy density should be from quantum field theory, they get a number that is off from the observed dark energy density by a factor of approximately 10 to the power of 120. That is 1 followed by 120 zeros. This has been called the worst prediction in the history of physics. The theoretical and observed values of vacuum energy disagree by more orders of magnitude than any other quantity in all of science. Something is deeply, pathologically wrong with our understanding. Which brings us back to James Webb and to a result announced in 2024 from the Dark Energy Spectroscopic Instrument, or DESI, which uses similar physics to what Webb can probe. DESI measured the expansion history of the universe using baryon acoustic oscillations, periodic density variations in the distribution of galaxies, imprinted by sound waves in the early universe that serve as another standard ruler. Their result, when they allowed dark energy to vary over time, what physicists call a dynamical dark energy or quintessence model. The fit to observations improved significantly compared to a fixed cosmological constant. What this tentatively suggests, and Webb's complementary data on early universe structure supports this direction, is that dark energy is not constant. It may be weakening or strengthening over cosmic time, a cosmological constant that varies. The implications for the fate of the universe are enormous. If dark energy is fixed, the universe expands forever in a big freeze. Galaxies recede beyond our cosmic horizon, stars burn out one by one over trillions of years, and eventually nothing remains but cold black holes slowly evaporating through Hawking radiation. If dark energy is increasing over time, the outcome could be a big rip, where the accelerating expansion eventually becomes so powerful that it tears apart galaxy clusters, then galaxies, then solar systems, then planets, then atoms, ripping the very fabric of matter to shreds in a cataclysm that ends everything in finite time. If dark energy is decreasing, or if it can change sign, the universe might one day recollapse in a big crunch or undergo a cycle of expansion and collapse called a big bounce. Some theorists even propose that a changing dark energy could trigger what is called a vacuum decay, a bubble of lower energy vacuum appearing spontaneously somewhere in space and expanding at the speed of light, converting everything it encounters into a different kind of physics. An end of the universe that passes through you like a wave, extinguishing all matter, all forces, all structure in an instant, with no warning. We do not know which of these futures awaits, but we know this. James Webb has made it undeniably clear that the simplest answer, a fixed cosmological constant, is increasingly strained by data, and that the nature of dark energy is now one of the most urgent unsolved problems in all of physics. I want to pause for a moment, because I realize we have been moving through some heavy material: expansion rates, galaxy formation, dark matter, vacuum energy. And I want to make sure this does not feel abstract. Because it is not abstract. This is the most personal story there is. This is the story of how you came to exist. Let me put the numbers in context. You are made of atoms, roughly 7 octillion of them. That is a 7 followed by 27 zeros. The atoms in your body are predominantly hydrogen, carbon, nitrogen, and oxygen. Hydrogen was forged in the Big Bang. Carbon, nitrogen, and oxygen were forged inside dying stars, in the nuclear furnaces of stars far more massive than our Sun, which exploded in supernova, scattering their heavy elements across interstellar space. Those elements drifted through the galaxy for billions of years, before condensing into our solar system's protoplanetary disk 4.6 billion years ago, eventually becoming part of the rocks, the water, the atmosphere, and the living things on Earth. Every atom in your body was forged, either in the first minutes after the Big Bang or in the death throes of a star. You are, in the most literal possible sense, made of stardust. But here is what makes this even more extraordinary in the context of everything we have been discussing. The universe's ability to produce you, a conscious, self-aware, atom-cataloging, telescope-building, question-asking creature, depends on a series of physical constants and cosmological parameters that are tuned to extraordinary precision. If the strength of gravity were slightly different, stars would either burn out in millions rather than billions of years, too fast for life to evolve, or would never ignite at all. If the strong nuclear force were slightly weaker, carbon could not form in stellar interiors. If the cosmological constant were even slightly larger than it is, The universe would have expanded so fast after the Big Bang that matter could never have clumped together to form galaxies, stars, or planets. If it were even slightly negative, causing collapse, the universe would have recollapsed before a single star could form. Physicist Fred Hoyle, who incidentally coined the mocking term Big Bang, intending it as a dismissal, was so troubled by the fine-tuning of nuclear physics required to produce carbon that he predicted an unknown nuclear resonance state in carbon-12 before it was found experimentally. A resonance that, had it not existed, would have made carbon production in stars essentially impossible. Life as we know it would not exist. His prediction was confirmed. Hoyle called it a put-up job. His astonished way of saying the physics seemed almost designed. Now the fine-tuning of the cosmological constant is even more extreme. The observed dark energy density is around 10 to the minus 123 Planck units. The theoretical quantum prediction is 10 to the plus 0, unity. The ratio is 10 to the minus 123. For the universe to be habitable, the cosmological constant needs to fall within an extraordinarily narrow window. And it does, by a factor that makes winning a lottery jackpot look like a cosmic certainty by comparison. What does this mean? There are essentially two philosophically respectable responses. One, the anthropic principle. We can only observe a universe with physical constants compatible with our existence. Among all possible universes, perhaps the infinite ensemble of universes suggested by the multiverse hypothesis, we find ourselves in one with life-permitting constants because we could not exist in any other. No design required, no explanation required. It is a selection effect. Two, there is something more fundamental going on, a deeper principle of physics that we have not yet discovered, which explains why these constants have the values they do, a theory of everything that makes the cosmological constant and the strengths of all forces logically necessary rather than arbitrary. James Webb does not answer this question, but it deepens it. Because by revealing that our current cosmological model has significant errors, that the universe formed structure faster than we thought, that dark energy may be dynamic, that early galaxies do not behave as predicted, Webb is forcing us to revise the very parameters of the model, and every revision shifts our understanding of exactly how precisely tuned this universe really is. You are the universe becoming conscious of itself. Every question you ask about cosmology is the cosmos examining its own foundations. That is not poetry, that is physics. What if the universe is not 13.8 billion years old? What if it is twice that age, or 10 times? What if 13.8 billion years is just the age of the visible universe, the stretch of time since the last major transformation, and the cosmos itself has existed in some form for far, far longer? This is not science fiction. This is a serious peer-reviewed proposal published in a major astrophysics journal. In 2023, cosmologist Rajendra Gupta of the University of Ottawa published a paper in the Astrophysical Journal proposing that the universe could be as old as 26.7 billion years, almost twice the standard estimate of 13.8 billion years. Gupta's approach combines two heterodox but individually respectable ideas, the tired light hypothesis and a varying speed of light or coupling constants framework. The idea is that some of the cosmological redshift we observe in distant galaxies is not purely due to the Doppler-like recession of galaxies, but also due to photons losing energy as they travel vast distances, tired light. Combined with slowly varying physical constants over cosmic time, Gupta argues this could reconcile the existence of those anomalously massive, well-formed early galaxies that Webb found. If the universe is older, if those very early Webb galaxies formed not 500 million years after the Big Bang, but potentially 2 billion years after some earlier phase of cosmic history, the problem largely dissolves. There was simply more time for structure to form. Now, to be clear, Gupta's model is in the minority. Most cosmologists remain committed to 13.8 billion years. The tired light hypothesis, originally proposed by Fritz Zwicky in 1929, faces serious problems. It predicts that the time dilation observed in supernova light curves should not exist, but it does. And the CMB fits the Big Bang model's predictions with extraordinary precision. But there is a more mainstream version of the older universe idea that is gaining traction, and it comes from a concept called eternal inflation. In the inflationary cosmology model, developed by Alan Guth of MIT in 1980 and refined by André Linde with his chaotic inflation theory, the Big Bang was not the beginning of everything. It was the end of a period of extraordinarily rapid exponential expansion called inflation, during which a tiny quantum fluctuation in a primordial inflaton field grew faster than light, expanding by a factor of at least 10 to the 26 in less than 10 to the minus 32 seconds. In Linde's eternal inflation framework, inflation does not stop globally. It stops locally, producing what we call a Big Bang and a universe like ours, but continues to rage in other regions of a larger, eternal background space. New universes are constantly being nucleated, each with its own physical constants, its own version of the Big Bang, its own history. Our universe is one bubble in an eternally inflating multiverse that may have been going on forever. The implications are staggering. If the multiverse is real, and it follows mathematically from the most successful models of inflation, then the observable universe is not the universe. It is an inconceivably tiny region of a far larger, eternal cosmos. Our Big Bang was not the beginning of existence. It was a local event in an infinite sea of physics. Can James Webb test the multiverse? Not directly. By definition, other bubble universes are beyond our observational horizon, separated from us by regions of still inflating space, forever receding faster than light. But Webb can test the inflationary models that predict the multiverse. The spectrum of quantum fluctuations in the CMB, which seed the formation of all large-scale structure, should carry specific signatures of inflation. A slightly tilted power spectrum with a specific index called the spectral index ENS. Webb's observations of early large-scale structure, combined with CMB data, can sharpen constraints on what the inflationary potential looked like, and begin to discriminate between competing inflationary models that have very different implications for whether the multiverse is real. This is the frontier. We are trying to use a telescope to ask questions about infinity, and we are making progress. Here is a question that should keep you up at night. What happened before the Big Bang? The standard answer, the answer given in most textbooks and documentaries, is that this question is meaningless. Time itself began at the Big Bang. There is no before any more than there is a place south of the South Pole. To ask what happened before the Big Bang is like asking what is north of the North Pole. The question contains a category error. That answer, while mathematically defensible within classical general relativity, has never fully satisfied physicists. Because general relativity breaks down at the Big Bang, the equations predict infinite density, infinite temperature, infinite curvature of spacetime at the singular origin point, what mathematicians call a singularity. A singularity is not a physical object or event. It is a place where the equations stop working. It is a flag planted in the mathematical landscape that says, we do not have the right theory here. To understand the Big Bang, and what came before or instead of it, we need a theory of quantum gravity. A theory that merges the two great pillars of 20th century physics. General relativity, which describes gravity and the large-scale structure of space-time, and quantum mechanics, which describes the behavior of matter and energy at the smallest scales. These two theories are extraordinarily successful in their respective domains. They are also, mathematically, deeply incompatible with each other. Several quantum cosmology frameworks have been proposed. In the Hartle-Hawking no-boundary proposal, developed by James Hartle of UC Santa Barbara and Stephen Hawking, the universe does not have a beginning in time at all. Instead, time itself becomes imaginary near the Planck epoch, smoothly transforming into a spatial dimension. The beginning of time is like the south pole of a sphere, not a boundary or a wall, just a point where the spatial directions come together. From this framework, the probability distribution for the universe arising from nothing is calculable. In Alexander Vilenkin's tunneling from nothing proposal, developed at Tufts University, the universe literally quantum tunneled into existence from a state of no space, no time, no matter. Just as a particle can quantum tunnel through a classically impenetrable energy barrier, The universe as a whole can quantum tunnel from absolute nothingness into a small closed geometry, which then inflates into everything we see. Then there is loop quantum cosmology, an approach to quantum gravity developed by Abhay Ashtekar, Martin Bojewald and others, based on loop quantum gravity. In LQC, the Big Bang singularity is replaced by what is called the Big Bounce. At extremely high densities, near the Planck density of 10 to the 96 kilograms per cubic meter, quantum gravitational effects generate a repulsive force that prevents the singularity from forming. In LQC, the universe did not begin, it bounced. A previous contracting universe reached a minimum size and rebounded into our current expanding phase. The Big Bang was a big bounce. And then there is the most recent and most radical proposal, the CPT symmetric universe. Proposed by Neil Turok of the Perimeter Institute and Latham Boyle and Kieran Finn, this model suggests that there is a mirror universe on the other side of the Big Bang, a universe that is the CPT symmetric reflection of ours. CPT symmetry means charge conjugation, swapping particles for antiparticles, parity, mirroring in space, and time reversal, running time backwards, applied simultaneously. In this model, if you ran our universe backwards to the Big Bang and then continued, you would find an anti-universe expanding backward in time, a universe with the same physical laws, with antiparticles playing the role of particles, with time running in the opposite direction. Our universe and its mirror image extend infinitely in both temporal directions, with the Big Bang as their common origin, a point of minimum size and maximum symmetry, not a singularity. How does James Webb connect to quantum cosmology? Directly, through what cosmologists call primordial gravitational waves. Inflation, the rapid early expansion phase, should have produced gravitational waves, ripples in space-time itself, imprinted on the universe at its birth. Different quantum cosmological models make different predictions about the amplitude and spectrum of these primordial gravitational waves. The ratio of their strength to the strength of density fluctuations, called the tensor-to-scalar ratio denoted R, is a key observable. Webb's observations of early universe structure, combined with next-generation CMB polarization experiments like CMB-S4 and the Light-Bird satellite, will constrain R to extraordinary precision, potentially discriminating between models. We are, for the first time, building the observational tools to test theories of the quantum origin of the universe. And James Webb is one of the keys. In 1950, physicist Enrico Fermi was having lunch at Los Alamos National Laboratory with fellow physicists Edward Teller, Herbert York, and Emil Konopinski. The conversation drifted to reports of flying saucers in the popular press, and Fermi, with the almost casual genius that characterized his thinking, made a quick calculation and asked a question that has haunted science ever since. Where is everybody? This is the Fermi paradox, and in the context of James Webb's discoveries, it has become simultaneously more pressing and more mysterious. Here is the logic. The Milky Way galaxy is approximately 13 billion years old. It contains roughly 200 to 400 billion stars. A significant fraction of those stars host rocky planets in the habitable zone, the distance range where liquid water can exist on a planetary surface. By current estimates from exoplanet surveys, particularly the Kepler and TESS space telescopes, perhaps 20 to 40 billion Earth-like planets exist in the Milky Way alone. The Milky Way has existed for 13 billion years. Life on Earth arose roughly 3.5 billion years ago, relatively quickly after Earth formed. Intelligence emerged on the human timescale. The Milky Way had ample time to produce intelligent life billions of years before Earth even formed. Any civilization that arose just 1 billion years before us and developed space travel could, at even modest speeds, say 1% of the speed of light, colonize the entire Milky Way in about 10 million years. A tiny sliver of cosmic time. They could have come. They could have left signals. They could have reshaped stars and galaxies in ways we would detect. We see nothing. No signals, no artifacts, no megastructures, no visitors. The universe appears, to all our instruments, cosmically silent on the question of intelligence. This is the Fermi paradox, and James Webb changes the calculation in a profound way. Because Webb has confirmed that complex galaxy formation began much earlier than we thought. The universe had organized structure, the prerequisite for stars, planets, and potentially life, far earlier in cosmic history than our standard model predicted. Which means the window for the emergence of intelligence has been wider and potentially earlier than we estimated. The paradox deepens. But Webb has also made a direct contribution to the search for life through its extraordinary atmospheric characterization capabilities. One of Webb's designed science goals was to use a technique called transmission spectroscopy to analyze the atmospheres of exoplanets, planets around other stars. As a planet transits in front of its star, starlight filters through its atmosphere, and the specific wavelengths absorbed or transmitted create a fingerprint of the atmospheric composition. In 2023, Webb analyzed the atmosphere of K2-18b, a planet approximately 8.6 times the mass of Earth, orbiting in the habitable zone of a red dwarf star 120 light-years away. The results, published by Dr. Niku Madhusudan of Cambridge University and colleagues, indicated the presence of carbon dioxide and methane, as expected for a hydrogen-dominated atmosphere. But there was also a tentative detection, controversial but tantalizing, of dimethyl sulfide, or DMS. On Earth, DMS is produced exclusively by biological organisms, primarily marine phytoplankton. It is considered a potential biosignature, a sign of life. Madhusudan and his team were appropriately cautious. The signal was at the threshold of statistical significance, and DMS could conceivably have non-biological explanations in an exotic hydrogen-rich atmosphere that we do not fully understand. More observations are needed. Webb's follow-up observations of K2-18b continue, but the broader implication stands. Webb was built not just to peer back in time, but to peer across space, to take the first steps in an inventory of planetary atmospheres that over the next decade may reveal the chemical signatures of biological activity on other worlds. We are, for the first time in human history, on the technical threshold of answering whether we are alone. And here is the haunting connection back to the Fermi paradox. If Webb's galaxy formation data is right, if intelligent life had billions more years to develop than our models suggested, and if Webb ultimately finds atmospheric biosignatures on many exoplanets, then the Fermi paradox becomes agonizingly acute. Life is abundant, yet silence reigns. Why? The most unsettling answer is the Great Filter, a concept introduced by economist Robin Hanson in 1998. The idea is that somewhere in the development from primitive chemistry to galaxy-spanning civilization, there is an extremely improbable step. A filter through which almost nothing passes. If the filter is behind us, if the emergence of eukaryotic cells or sexual reproduction or multicellular life was the extraordinary improbable step, then we may be among the very few to have made it through, and the silence makes sense. But if the filter is ahead of us, if intelligent civilizations routinely hit a wall, a self-destruction event, an insurmountable barrier on the road to the stars, then our success so far is no guarantee of what comes next. Webb cannot tell us where the filter lies, but it is gathering the data that will begin to answer whether life is rare or common, and the answer will tell us something profound about our own future. Let me be honest with you about something that popular science communication often gets wrong. Scientists are not a monolithic block. They argue, they disagree fiercely, they have careers and reputations tied to particular models, they are human, and the debate around James Webb's anomalous findings is no exception. There are broadly three camps in current cosmological debate. Camp 1, the conservative wing. These are cosmologists who believe that the lambda CDM model is fundamentally correct and that Webb's anomalies will be explained by refinements to our understanding of baryonic physics, the complex physical processes involving ordinary matter, star formation, stellar feedback, supermassive black hole feedback, and gas dynamics. In this view, our models of galaxy formation were too simplistic, not wrong at the foundational level. We simply underestimated how efficiently early black holes and young stars could drive gas compression and trigger rapid star formation in early protogalaxies. The leading voice in this camp is arguably Dr. Mike Boylan-Colchin of the University of Texas at Austin. who has done careful statistical work showing that a subset of the most extreme Webb galaxy candidates do seem to challenge even generous extensions of the lambda CDM framework. But he also notes that many of the impossible early galaxies become less impossible once uncertainties in photometric redshift estimates and stellar mass estimates are properly accounted for. He advocates for patience and more data before abandoning the standard model. Camp 2, the reformers. These are cosmologists who believe lambda CDM needs significant modifications, not replacement but extension. They accept the core framework of the Big Bang, inflation, dark matter, and dark energy, but argue that the specific parameters and physics governing each component need substantial revision. In this camp, dark matter might be fuzzy rather than cold, inflation might have proceeded differently than the simplest models suggest, and dark energy might be dynamical rather than a fixed constant. Dr. Priyamvada Natarajan of Yale University exemplifies this approach. Her work on high redshift black holes, including the proposal that direct collapse black holes seeded the first quasars, represents exactly the kind of reformist thinking that takes Webb's anomalies seriously, while working within an extended lambda CDM framework. Camp 3, the revolutionaries. These are cosmologists and physicists, a minority but a vocal one, who believe Webb's data is symptomatic of a deeper structural failure of our cosmological paradigm. Not just a parameter adjustment, but a need for a genuinely new foundational framework. Eric Lerner, plasma physicist and author of The Big Bang Never Happened, has used Webb's data to argue for a non-expanding universe based on plasma cosmology. His paper claiming Webb showed the Big Bang did not happen went viral on social media in 2022. Most mainstream cosmologists strongly reject his interpretation. The CMB alone provides overwhelming evidence for the Big Bang, and the paper was widely criticized for misrepresenting the scientific consensus. But it illustrates the cultural moment. Webb's anomalies have created enough uncertainty that alternative cosmological proposals are getting a wider hearing than they have in decades. More credible within the mainstream is the work of cosmologists like Stacy McGaugh of Case Western Reserve University, who has been one of MON's most rigorous defenders for decades. McGaugh has published extensively showing that MOND makes precise parameter-free predictions for galaxy rotation curves, and the Tully-Fisher relation that match observations with remarkable accuracy, often outperforming dark matter models that have multiple free parameters. His argument is not that lambda CDM is wrong about everything, but that its handling of the galactic scale physics is fundamentally misguided. And then there is the Hubble tension camp, led by Adam Rees himself, a man who, having won the Nobel Prize for discovering dark energy within the lambda CDM framework, is now one of that framework's most prominent critics. His position is nuanced. He does not claim the standard model is wrong, but he has been clear and public that the Hubble tension is real, is statistically significant, and requires either new physics or a systematic error in the CMB-based calculations that no one has yet identified. So where does this leave us? Honestly, in a beautiful, exciting, terrifying position of uncertainty. The data is real. The tensions are real. The anomalies are real. The explanations are contested. And the next 5 to 10 years of observations, from Webb, from future CMB surveys, from the Vera Rubin Observatory, from the Euclid Space Telescope, from next-generation gravitational wave detectors, will begin to settle these questions. We are not at the end of cosmology. We are at one of its most electrifying inflection points. I want to tell you something about science that is rarely said plainly. It has a perfect track record of being wrong. Every single major scientific framework in history has eventually been revised, extended, or replaced. Aristotle's cosmology, Earth at the center, perfect crystalline spheres carrying the planets, unchanging heavens, was the scientific consensus for nearly 2,000 years. Ptolemy refined it into a beautiful mathematical system that predicted planetary positions with reasonable accuracy. It was wrong. Copernicus replaced the geocentric model with a heliocentric one. He was right about the center, but wrong about the orbits. He kept perfect circles. Kepler corrected the circles to ellipses. Galileo provided telescopic evidence. Newton unified terrestrial and celestial mechanics in a single framework of gravitational force that stood unchallenged for over 2 centuries. Newton was wrong, or rather, incomplete. Einstein showed that gravity is not a force, but the curvature of space-time, and that Newton's equations are an excellent approximation for weak fields and slow speeds. Is Einstein wrong? He may be incomplete. The singularity at the center of black holes, the singularity at the Big Bang, and the incompatibility of general relativity with quantum mechanics all suggest that Einstein's framework, glorious as it is not the final word. This is not a flaw in science. It is its greatest virtue. Science is the only system of knowledge humanity has ever developed that builds in its own mechanism for self-correction. That is designed to fail better, to identify its own errors and transcend them. The history of science is the history of successful betrayals of previous certainty. The philosopher of science Thomas Kuhn, in his landmark 1962 book, The Structure of Scientific Revolutions, described the pattern that James Webb's findings exemplify. Normal science, the period when a paradigm, an accepted theoretical framework, is in place and scientists work within it, solving puzzles, accumulating data. Then anomalies appear, findings that the paradigm cannot explain. Initially, they are dismissed, attributed to measurement error or experimental noise. But as they accumulate and resist explanation, a crisis builds. Scientists begin to question the foundations. Eventually, a revolutionary period arrives. A new paradigm is proposed that explains both the old data and the anomalies. The old paradigm does not disappear overnight. There is resistance, generational change, but eventually the new framework becomes the new normal science until the next revolution. Kuhn called these transitions paradigm shifts. We may be living through one right now in cosmology. The anomalies, the 2 massive early galaxies, the Hubble tension, the early disk galaxies, the anomalous supermassive black holes, are accumulating. They have not yet triggered a recognized revolution. The standard model has not yet been replaced. But the crisis phase Kuhn described, the phase of anxiety, of competing alternatives, of accelerating questioning, is unmistakably underway. And here is what is so remarkable about this particular moment. The crisis is being driven by a machine, by a technological achievement, by 30 years of work, by thousands of engineers, scientists, and technicians who built a telescope that could see things no human eye had ever seen. The James Webb Space Telescope is not just an instrument of astronomy, it is an instrument of epistemological revolution, a tool for knowing that we were wrong about things we thought we knew for certain. In 1610, Galileo pointed his crude telescope at Jupiter and saw 4 moons orbiting it. In an instant, the idea that all celestial bodies orbited the Earth was broken. Today, James Webb has pointed its golden mirror at the infant universe and seen galaxies that should not exist. The details are different. The structure is the same. Observation overturns theory. Reality defies expectation, and we are richer for it. There is a Japanese concept, wabi-sabi, which finds beauty in imperfection and impermanence. There is a scientific equivalent, a kind of intellectual wabi-sabi, in being wrong. To discover that your model was incomplete is to discover that reality is richer than you thought. Every scientific error that is corrected is evidence that the universe has more to show us than we imagined. The NASA insider, who says, "We were wrong about the universe," is not confessing failure. They are announcing discovery. We started this video with a shock. A NASA insider, a real credentialed scientist, saying that we were wrong about the universe, about its history, its structure, its age, its contents, its fate. Now, after more than 2 hours together, I want to show you that the shock was not the point. The shock was the door. What is on the other side of it is something far more interesting and far more valuable than any single revelation. Let me bring together everything we have explored. James Webb found galaxies in the early universe that are too massive, too organized, too complete to have formed in the time the standard model allows. This tells us that either our model of galaxy formation needs fundamental revision, or our model of the early universe itself The parameters of dark matter, dark energy, inflation is incorrect. Possibly both. The Hubble tension, the fact that two exquisitely precise measurements of the universe's expansion rate disagree by a statistically irreconcilable amount, suggests that somewhere in our understanding of cosmic physics, there is a deep error. Whether it is in the physics of the early universe, the nature of dark energy, the behavior of dark matter, or something entirely unknown, a number that should be the same is not the same. The universe is contradicting itself. Dark matter, which we have never detected despite extraordinary efforts, may not be what we think. It might be fuzzy quantum fields rather than particles. It might not exist as a substance at all, but be an artifact of incomplete gravitational physics. Dark energy, which constitutes 68% of the universe, may not be a cosmological constant, but a dynamical field, quintessence, evolving over time, with implications for the ultimate fate of all structure, all stars, all life. The universe may be far larger or far older, or far more cyclical than our single Big Bang model suggests. Eternal inflation may mean that our observable universe is a bubble of special physics in an infinite, eternal ocean of different physics. The question, why does the universe have these physical constants, may ultimately be answered not by deep theoretical necessity, but by anthropic selection. We are in a life-permitting bubble because life-permitting bubbles are the only ones that generate observers to ask the question. And woven through all of this is the possibility, not certain, not confirmed, but scientifically credible for the first time in history, that the first whisper of another living world has reached us through the atmosphere of a planet 120 light-years away. What do you do with all of this? I want to suggest that the broken universe, the universe of tensions and anomalies and models that do not quite fit, is actually a gift. Because here is what the history of science teaches us, over and over again. The places where models break are the places where reality shines through. The places where our equations fail are the places where the universe is most insistently trying to tell us something new. The Hubble tension is not a problem. It is a message. The early massive galaxies are not anomalies, they are clues. Every place where James Webb contradicts our models is a place where the universe is saying, "You haven't understood me yet, keep looking." There is something called the Ptolemaic danger, my term for the trap of building an ever more complex version of a fundamentally wrong model in order to preserve it. Ptolemy's geocentric astronomy became extraordinarily complex. Epicycles on epicycles, equants, deference, precisely because its foundational premise was wrong and required increasingly elaborate patches. For decades, cosmologists have been adding complexity to the standard model. Dark matter, dark energy, inflation, baryonic feedback parameters with many adjustable dials. Webb may be telling us that the complexity has reached a Ptolemaic tipping point, that Copernicus is waiting in the wings. That next Copernicus, who will write the equations of a new cosmology that explains Webb's galaxies without requiring impossible formation rates, that resolves the Hubble tension naturally, that gives us a physical understanding of dark energy and dark matter, will be someone alive today. Perhaps someone studying physics or astronomy right now, watching videos like this one, absorbing the anomalies, feeling the discomfort of an unsatisfying model. Maybe that person is you. But let me take this further. Let me make this not just about science, but about how you navigate a world that is constantly revising its certainties. We live in an age of information overload, of certainty markets, where pundits, politicians, algorithms, and media ecosystems sell you confidence. They offer simple models of complex realities. They provide the emotional comfort of a settled worldview, and they quietly punish you for uncertainty, for nuance, for saying, "I don't know." James Webb is the greatest reminder in a generation that I don't know is not weakness, it is accuracy. The most respected cosmologists on Earth, looking at the best data ever collected about the universe, are saying, "We were wrong, and we are not sure in which direction yet." That intellectual humility, that willingness to let the data reshape the model rather than reshaping the data to fit the model, is the highest form of rational courage. Think about how you apply that to your own life. How many of your fixed beliefs about people, about yourself, about what is possible, about how the world works, our Ptolemaic systems, elaborate, self-consistent, internally logical, but built on a wrong foundational premise. How many of your certainties are models waiting for their James Webb moment? The universe at 13.8 billion years old, or 26.7 billion years old, or infinitely old, depending on which model survives, has been running experiments for longer than human language has existed, and it is still surprising us, still producing data that none of our models predicted, still being stranger and richer and more complex than our best attempt to describe it. That should be an invitation, not to despair at the extent of our ignorance, but to marvel at the guarantee that there is always more to discover. Always another layer, always another Webb moment, waiting to overturn the next certainty. Let me do something now that I promised at the beginning. Connect every major idea we have discussed into a single coherent revelation. 14 billion years ago, or perhaps longer in an earlier phase of cosmic history, a quantum fluctuation in a primordial field initiated a period of explosive inflation. Inflation imprinted the seeds of all future structure on the fabric of space-time. Tiny quantum wrinkles that would grow under the gravitational influence of dark matter into the first protogalactic clouds. But those clouds collapsed and formed stars and galaxies faster than our models predicted. Dark matter, whatever it truly is, organized the architecture of the cosmos more efficiently than cold dark matter models anticipated. As galaxies formed and supermassive black holes grew at their centers, a mysterious energy, dark energy, threaded through the vacuum of space. Not fixed, perhaps, but evolving. In the early universe, it may have behaved differently than it does today, contributing to the Hubble tension between early universe and late universe measurements of cosmic expansion. Over billions of years, in one corner of one galaxy, a medium-sized star formed. Around it, a rocky planet at just the right distance for liquid water. Life emerged, slowly at first, then explosively. One species of those living things developed language, mathematics, fire, and eventually technology. They sent a machine into space, a hexagonal gold-plated eye that looked back at the beginning of everything and said, "This is not what we expected." That species is us. That machine is Webb. And that moment of not what we expected is not the end of the story. It is the beginning of the next chapter. You are not a passive observer of this story. You are part of it. The atoms in your body carry the history of the universe. The neurons firing in your brain as you process these ideas are the universe reflecting on itself. The curiosity you feel, that itch to understand, to go deeper, to ask the next question, is the most cosmically significant force I know of. It is the force that built the James Webb Space Telescope. It is the force that will build whatever comes after. Here is the empowering truth at the heart of everything we have discussed today. The universe does not need to be fully understood to be deeply meaningful. The Hubble tension does not diminish the beauty of a starry night. The mass anomalies of early galaxies do not make your relationships or your work or your love less real or less significant. In fact, knowing that the cosmos is stranger and richer and more uncertain than we thought makes the 13.8 billion years of cosmic cooking that produced you all the more remarkable. You are not an accident. You are a necessary consequence of the laws of physics as they exist in this particular universe. Laws that are fine-tuned, whether by design or by anthropic selection, to produce complexity, chemistry, biology, and consciousness. The fact that we cannot explain exactly why those laws have those values is not evidence that the laws are arbitrary. It is evidence that our understanding is incomplete, and incomplete understanding is the precondition of all growth. Carl Sagan said, "The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself." Richard Feynman said, "I would rather have questions that can't be answered than answers that can't be questioned." And now, a NASA insider, a working scientist at the frontier of human knowledge, looking at data from a $10 billion telescope, says, "We were wrong about the universe." That is not a defeat. That is the sound of science working exactly as it should. That is the sound of a species that has not given up on truth, even when truth is harder to find than we thought. Even when the universe is stranger, older, richer, and more uncertain than our models predicted. That is the sound of us looking up. Before I go, let me give you something actionable, something you can do right now, tonight, that connects you directly to everything we have talked about. Go to the James Webb Space Telescope's official image gallery at jwst.nasa.gov. Look at the image called Cosmic Cliffs, the edge of the star-forming region NGC 3324 in the Carina Nebula. In that image, you will see pillars of gas and dust, towering hundreds of light-years tall, sculpted by the radiation of young, massive stars. Stars being born right now as you look at them. The image looks like a mountain range at sunset. It is, in fact, a stellar nursery 7,600 light-years from Earth, captured in the first week of Webb's science operations. Now look at the Webb Deep Field, the first deep field image released in July 2022, which covers a patch of sky smaller than a grain of sand held at arm's length. In that image, you will see thousands of galaxies. Some of them are the oldest light ever captured. Some of them may be among the anomalously massive early galaxies that are rewriting cosmology. You are looking at the beginning of time. And when you look, know this: every single point of light in that image represents a collection of hundreds of billions of stars. Every one of those stars potentially hosts planets. The universe is so much larger, so much richer, so much stranger than any map we have built of it. And we are just getting started. We began this video by asking what happened when one telescope broke the model of the cosmos. We traveled through the impossible early galaxies that should not exist, through the Hubble tension that says the universe cannot agree with itself about how fast it is expanding, through dark matter that may not be what we think it is, through dark energy that may be changing, not constant, through the quantum origin of the universe and the possibility of a multiverse stretching beyond all observational horizons. We asked what this means for life beyond Earth, whether those atmospheric molecules on K2218b are the first distant echo of another living world. We went inside the scientific debate, hearing from the conservatives, the reformers, and the revolutionaries. We examined the history of scientific error and found it beautiful rather than shameful. And we ended here, with you made of star stuff, a child of a universe that is older and stranger than its current map suggests, holding the questions that the next generation of telescopes and the next generation of scientists will spend their lives answering. Those scientists might be you. Those telescopes will see even further than Webb, and the universe will keep being more extraordinary than we predicted. I hope you feel right now exactly what I feel every single time I look at the Webb images. A mixture of awe, humility, wonder, and profound gratitude. Gratitude that we are alive at this moment. Gratitude that we have built machines that can see 13 billion years into the past. Gratitude that the cosmos is still surprising us. Thank you for spending this time with me, genuinely. You did not have to watch a 3-hour video about cosmology. You chose to. That curiosity, that choice to go deeper, is the most human thing there is.